So that's online. I will introduce you the directional derivatives, which this was not taught last year, but I think it's interesting and it's essential for Lyapunov theories. Okay, so it's kind of complementary materials. And then we'll discuss what is global, semi-global, and local stabilities, and Lassalle's theory, which is similar to the invariant sets theory. So we have covered this, which is that this is a quadratic function. C1, C2 are the coefficients. So any type of this function can be considered as a Lyapunov function, which is positive definite, right? And the configuration is like this, which is 0 at 0. So 你们回去都有复习吗？上次讲 So is that okay for the lecture we taught on last Wednesday? Is that okay? 你们都 OK 吗？回去都有复习吗？好，没关系，我们今天会再教一次哦，那就最后一次了，就是从不同角度。And so, okay, here are some questions. If Z is PD, which means that the only intersect with the origin is when at 0 at 0, right? Where Z is 0 and X1, X2 are 0. And if Z is some constant, then all the X1, X2 satisfy this condition is considered as a level set, right? So it's like you take a slice on this shape, they will give you like a circle, right? If C1, C2 are 1, 1. And this circle is the set which are the possible location of X1 and X2, right? Because those X1 and X2 are satisfying these conditions, okay? But the greater the Z values doesn't implies the greater the norms, right? These two have different meanings, right? 对不对？这个是 Z 方向。This is in the Z direction. This is in the horizontal directions. Or you can consider the Euclidean distance of the state to the origin, right? Usually we only care about these terms, right? Because when we discuss the stability, stable, unstable, or asymptotically stable, the definition is all about the norm of X. We say stable, what's the meaning or the definition for stable? We say X1, X2. The first portrait for a stable system is like you start from here, and it's not necessary for the trajectory converge to the origin, but it remains bounded, right? Remain bounded in some distance. If initial condition is satisfied, if your initial condition is around the equilibrium point, then the solution is also around the equilibrium point by some epsilon. Then it's defined as stable, right? So this radius is considered as epsilon. Okay, and this is smaller than delta. Okay. And the radius of this disk is epsilon. So it starts around or near the equilibrium point, the trajectory, the xt will remain in a certain distance. That's called stable, right? But for the symptotically stable, it has to converge to the origin, right? So stable, if this is stable, the set of stable, then a symptotically stable is in the set of, if it's asymptotically stable, it must be defined as stable, but not vice versa, right? 对吧？反过来就不一定了嘛。As entirely stable 一定是 stable， 但 stable 不一定代表它会 as entirely stable 嘛，因为它 converge 到 zero。Okay， so only when we define this stable, the definition for stable, we all discuss about the norm of your states, your norms of your states, not about the above functions or the z functions, right? Because it's virtual. But all we care is physically what's the state to the origin. But unfortunately, we don't know the trajectories. That's why we are not sure about this. But this is known, right? This z function can be determined, right? But it's not, you cannot say, oh, if this z is greater than this z, then their argument the norm of the argument will be the same. Not really, okay? Then we talk about how the z function changes with time, right? And it depends on your trajectory x1 and x2, depend on your dynamics. And that's the time when we can introduce the directional derivative. So what is directional derivative? Imagine that in this 2D plane, okay, in this 2D plane, you consider it's a phase portrait. And in this surface is like a Lyapunov function. It is in the like z direction, okay? The higher the value, the greater the Lyapunov function. This is similar to this cone. So what is directional derivatives? This is nothing about Lyapunov function, just definition for directional derivatives. And this has been covered in your engineering mathematics in your undergrad. So what is directional derivatives? Here it says f is this function, this Lyapunov function, or in the function in the z direction, okay? So it defined as how does f changes as the input shift in the direction of vector v. So the direction of vector v is defined on this phase portrait, okay? It's a 2D dimension. It defined as the dynamics of vector field, okay? 我们现在就要看说，这里有一个点 ，OK？ 当它从这边 move 到这边的时候，它投影的这个值变化了，在这个方向变化了多少，懂吗？所以当我往 v 方向移动的时候 ，f 会变化多少 ？OK？ We're trying to see when it moves from here to here along the v direction, okay? Which is kind of the dynamics, right? Your x dot, right? When it moves from here to here, what's the change of f value, which is from here to here? And obviously, it's increasing from here, right? So this is called directional derivatives. If we consider z direction as v, okay, x1, x2. So in this plane, x1, x2 is phase portrait, right? Given some dynamics, if x is here, you have some direction here called x dot. It is a column vector. It's a vector, right? In the 2D plane. So this is the dynamics at this location, at these states, right? And if you define some nimble functions or some whatever functions, this function have given some x in the 2D plane, you can find a corresponding value v, right? V x1, x2. And when you move to here, it's another v x1 prime, x2 prime, okay? So how do you define the change of v? So I would say with respect to time, the change of v is v dot, right? Okay. So this only discuss the change of v with respect to time, but we have dynamics here, 对不对？我们有动态啊。And dynamics So we somehow you need to, we want to see, so the role of this vector come into play, right? Obviously from this figure, this rule arrow come into play, right? So, and it's the dynamics. So somehow you need to put dynamics into here, right? And that's the chain rule come into play. So you can put whatever variable you like in here, right? And in this system, because we care about dynamics, so of course you need to put x here, because this is dynamics. So, and you have to put x here. So this is dynamics. Okay. So the and basically is so basically this is the concept of directional derivatives. Okay, this is derivative, right? And along this direction. Okay, this is derivative along this direction. 这样懂吗？我要看 v 的 derivative 在你动态移动的方向，因为动态决定我这个 state 往哪边走嘛。那我要看它走的时候，我的 v 我自己创造这个虚拟的 v 它是增加还是减少 ？OK， 你可以想成是它是能量。如果往这边走，我找到这个 v 呢，它会递减，那有可能就是 stable， 这样懂吗 ？So here, this is the direction, okay? And this is the gradient. Gradient represents the slope at this point, and it's 2D, so it's a surface. It's a normal of this surface. 懂吗？所以这样乘起来就会是它随时间的变化是多少了？那这个是已知嘛？给定什么动态系统，我就带什么进去，这样。So you can design. So this is determined, right? This depends on what your dynamics is. If you are controlling car, robots, it's defined, right? It's defined as this. It's defined. You cannot do. You can do nothing with it. But you can redefine this v, right? If this, okay, if you don't like this v because it doesn't guarantee that beta is negative, you can find another v. You can recreate another v, okay, maybe like this shape. And maybe this v, this new v, give you these conditions. Okay, 这样懂吗？ But in these two cases, the dynamics never doesn't change. Okay. 好，这个就是 directional derivatives。这个有点像你爬山，你就是第二波方程有点像，就是这是我山，你没有办法改变山的形状嘛？对，山的形状，比如说你在某一个山腰处，它的斜坡长度就是这个 gradient， 就是它的 slope 嘛。这个山有多陡，你没有办法改变山嘛，但是你能改变什么？我要往哪边走嘛？那这个就是往哪边走嘛，往哪边走嘛？那你往不同方向走，你山高度是会下降的程度不一样，对不对？就是这个原理。那如果你一直往那这个是动态，就决定你怎么走了。那如果你走不管在什么山的走法都是一样的话。抱歉，我再重新讲一次。如果你这样走的话，你在某座山沿着你的 motion pattern 走，那你发现你高度一直在递减，递减到最后你会到哪里？地狱吗？不会嘛，因为它是 positive definite， 最低就是到0嘛，就是到地面而已。那你到地面的话，这种 configuration 是保证你一定是到原点，这样就是 stable， 这样懂吗？这样懂吗？这样比较好理解吧？ 所以我没办法改变这个，但是我可以改变 v， 就是说我的走法不变的话 ，maybe 我在这座山不适合我，我没办法 guarantee 我 always 都是下山，有时候可能会变上坡，因为山的形状不一样，这样懂吗？因为你走的路径是不变的嘛，你走的方向是不变，在不同点我的 vector 是指向不一样的地方，这样懂吗？ So I just say the analogy of this label function is like mountains. When you go hiking in the mountains, this is at any location here around here. This is the slope of the trail, right? And you can go any directions, and the direction is determined by your dynamics, right? And assume at this time I want to go this direction. And if you follow this direction, then you know that your altitude is declining. That means that eventually you will get to the sea level, right? Because of this mountain, the shape configuration of these mountains. The only location at 0 is the origin, right? When height is 0, the only location is the origin. And you know this system is entirely stable, right? Even though I don't know what's the motion pattern of some dynamics, but I know the height is always decreasing. Eventually I'll get to the sea level, which is the origin, right? The analogy is this. But if I use the same motion pattern, okay, and for different mountains, I choose different label functions. Maybe mountain 1 doesn't always guarantee this, and I choose a different mountain, and this condition always holds no matter where I am. Then it's a good label function. So, but the dynamics is the same one, right? So it's a sufficient condition, not necessary. If you find one, that's fine. But you did not find one, that doesn't mean this system is unstable. You can keep continue find a new one, a new V, okay? So I think it's clear. So here is the same, similar to what I just said. Given a dynamic system, right, you can plot the phase portrait, which represent the dynamics. And again, it could be unknown, okay? Because you don't know the solution. It's nonlinear ODE. You don't know the trajectories, but you know that every point, what is the direction it's trying to go, okay? So it's physically exist. But what doesn't exist, or what is virtual, is this label function, right? And in this case, the label function is kind of this shape, okay? And this is the phase portrait, which is lying in this 2D plane, okay? Okay. And these 3 circles are the label surface on this phase portrait, and the projection is this 3, okay? So imagine that if you, according to this dynamics, the trajectory is this, right? Label function is this. And you can see in this case, V is always decreasing, right? When you get here, V is what? When you get here, V is 3, right? So this label set represents V is 3. And when you follow these dynamics, the trajectory is here. And you know that after some time period, V is 2, right? In this circle, V is 2. So V always decreasing until you reach the origin, right? But for the same dynamics, I choose a different label function, which is for here. Okay, what happened is, I know it's V is 3 here. Okay, V is 2 here. 2 here, right? And V decrease because it's inside this label set, right? So so this is a label set, and the label set inside this bigger label set will be, the value will be smaller than this one, okay? The smaller size the label set, the smaller the value of V, okay? So 这样懂吗? Okay, so when here is V2, right? And you go inside, and I know at this point, or this point, V is smaller than 2. But when it reaches to here, V is equal to 2, so V increase, right? So this is not a good diabolical function. And the previous one, this one is better than the next one. Because V dot is always negative. V is always decreasing. But it's the same dynamics, right? This yellow line never changes, right? It's identical in these two examples. So the problem is, how did you find V? Well, try. Okay, just try. But if it's a linear system, and as I say, you can use linear matrix inequalities. Okay. And that's not covered in this course. So next, is any question before we get to the next slide? 没有任何问题。哎。Try Or another way you can do is, if it's really hard to find V, you can change your F by design U. Okay. For example, if your dynamics minus x squared plus 5, you can say, oh, I add another U, and U define as minus 5. Okay. Then your new F, new closed loop system is squared. Okay. But it's a very simple case. Usually, it's very nonlinear. Okay. Semi-global and local stability. So global stability means for all initial conditions. Remember, all initial conditions. It's all about initial conditions. And for semi-global, it's all initial conditions provided that another condition is the gain are selected appropriately. Appropriately means depends on the initial condition. Okay, initial condition. I see. Okay. And local stability means for some initial conditions. Okay, for some. So for example, for global stability, if you find a V and you find your V dot after you substitute your closed loop dynamics, okay, you have this V dot, which means what? For any x, no matter what the x is, this V dot always is negative definite, right? 对不对？不管你 x 在哪里 your V dot is always negative. 那这样除了原点以外，那这样它一定是 global stability, because no matter where x is, V dot is negative, so it's always stable. Okay, so it's global stability. So for semi-global, the example is this one. Okay, K is the control gain, which is the parameter you can select. Like if, for example, K is minus in the control, this K is in the control. Okay, you can select whatever K you like. Okay. In this case, as long as the part inside the bracket is greater than 0, V dot is negative, definitely. Okay. So to ensure this is positive, it depends on the initial condition of x, right? So given if x initial condition is 2, this is what? 4, right? 2 squared is 4. Then you have to select k greater than 4 to make sure this one is smaller than this. And the summation will be greater than 0. And V dot will be negative, definitely. So this k, provided that the gain are selected properly, means it depends on the initial condition. And for local means not this and not this. Okay. it only convert, the stability only guaranteed if you start from some local region, not anywhere. Okay. So for example, the global case is if you start from some point x0, it might be stable or converge to the origin, or converge to the origin. Okay. For semi-global, you need to choose a k greater than some value. So if your k is 1, if k is 1, it might go diverge. Okay. If k is 1, then only any initial condition in this range will be stable. So you can increase k to be 2. Wait, hello? You can increase k to be 2 to enlarge the domain of attraction. Then you cover this initial condition. Okay, this domain covers this initial condition because you increase the control gain k. So this now included in the domain of attraction, so it can converge to the origin. Okay, 懂吗? So this domain can be controlled by the size of domain can be controlled by the control gain. Okay, so this is semi-global. For local, you cannot do anything. Okay, for local, it means that if your initial condition is in here, and it can the guarantee that the path of solution can converge to the origin. But if you are in here, it will diverge. Okay, 这样懂吗？没有问题。So it's all depend on the initial condition. Okay, and you can tell from what V dot looks like. Now, let's give you an example how you can use stable function to prove the stability. So consider an pendulum case. Okay, pendulum can move around this joint, and this ball is connected by this rod. Okay, so this is the governing equation, and we negate the mass of this rod. Okay, just consider the mass of this ball. So this is governing equation. Okay, from the dynamics. Okay, 从动力学你可以知道这个东西，对不对？ So and use this governing equation, you can write down its dynamics. Okay, in the state space form. Okay. So now your state is x1, x2. x1 is the angle. x2 is the angular velocity of this angle. Okay. So question is this system stable? Stable or unstable or asymptotically stable? You can solve the solution probably, I don't know, but can you tell from the dynamics prove that it's stable, unstable, or asymptotically stable? Pretty challenging, right? And what you can do is use the stable function designed as this. And is this stable function PD or PSD? Is it 0 at 0? Or is it 0 only at 0? Right? Because if your x1 is equal to what? 2 pi, right? 2 pi is not at the origin. More than one equivalent point can make this v to be 0. So it's not a good choice for this to be a default function. But here, just for example, so here x1 is theta, x2 is theta dot. X2 minus right? Now you take the time derivative of v. x defined as x1 and x2. So you can imagine this will be a row vector, this will be a column vector. 对吧? So what's this? This is from dynamics. Okay. It's a column vector and this will be a row vector. What's this? So it's v x1 x2, right? So what's this? The derivative with respect to x1. This is x1. Okay. x1. So there will be g L sin theta. Correct me if I'm wrong. And this is x2. 对不对? Right. Or g L sin x1. Maybe I just change to x1. So let's make the whole process simpler. x1. Okay. So this is known. So what is v dot? V dot will be 0. Okay. So this times x 1 dot, right? This times x2, which will be g L sin x1 times x2 minus 这个乘以这个乘以这个，也就是 x2。Right? So it's 0. What happens? What happens? It's moving, right? The dynamics is not 0. 对吧? If you substitute, consider x1 is pi over 3. 想想看，如果 x1 是60度的时候，你放开会怎样？它是会动。会动的话 ，v theta 是0吗？好像不太会，对不对 ？Okay, so something wrong. But you can conclude it's stable, right? Because v dot is 0, which implies v is constant. V is what is v is constant? Level set, right? The solution lie in the level set. 对不对? So it's stable. It doesn't go anywhere. It doesn't converge to 0, but it doesn't go anywhere. So it's stable, right? 这样有没有问题? So in this example, the best you can conclude is stable. Because we don't put any. So here is only we don't have any friction here. There's no friction, so the energy doesn't go anywhere. Okay. It's free motion. There's no friction. Okay. So it makes sense for v to be constant or v dot to be 0. Right. It just oscillate forever. Right. So in this case with friction. So here is the previous one is without friction. Now we add some friction here. Okay. The friction is inverse proportional to the velocity. Okay. 我们加一些阻尼，去消耗它一些能量，看看它的 v dot 会是怎样。So after you added this term and you evaluate v dot, this v dot give you this. So now is v dot nd or nsd? ND? Raise your hand if it's ND. If you think it's ND. How about NSD? Okay, NSD. Why? Why? If you look at here, it's x1, x2, right? V is a function of x1 and x2, right? But here, V dot is function of what? X2. Where did x1 go? Nowhere, right? Not nowhere. X1 can be any value which doesn't change V dot, right? So that means x1 could be 0, could be non-zero. If x2 is 0, V dot is 0, right? If x2 is 0, V dot is 0. But x1 could be 0 or non-zero. It doesn't care. We don't care, right? They don't change V dot, right? So that means not only the origin can make this one to be negative definite. 听得懂吗？不止00，所谓00就是说 x1 0 x2 0，不止00会让它是0。OK， 10 20 30 40，只要这个是0，它就是0。但 x1 呢，任意数，对不对？所以它不是 ND， 它不是 ND， 它是 NSD。So the best you can conclude is stable because x1 is not constrained. x1, no matter what x1 is, this one V dot will be negative till x2 is 0. 这可能有点难想象嘛。So V will not converge to 0. V, as long as x2 is 0, V will be a constant, which is not 0, because x1 might not be 0. 听懂吗？知道我讲什么？ x2 如果是0，它就是0的，对不对？好，如果 所以如果 x2 是0的时候 ，v 是就是 v 大是0，所以 v 就 constant 了。这个 constant 会是0吗？不会嘛，因为 x1 呢，这个是 constant 的时候表示好 x2 是0嘛 ，x2 是0，不代表它就是0，因为它有 x1 啊。那 x1 没有在这里面，因为 x1 不影响它的变化率，这样懂吗？懂我意思吗？这样是很难想象，所以它图长这样。So what does the V looks like? V, this is V. Let's say if x2 is 0, V dot will be 0. V is constant. Right? Okay. Okay. And not necessarily 0. Because x1 might not be 0, right? Because if x1 is not 0, right? This might confuse you. So if you think V2 is 0, this is 0, so is that clear? If x2 is 0, it only means V is a constant, which is not necessarily 0. Okay. 因为 V 大是0嘛 ，V 不变的嘛 ，V 不变不是 constant 吗？1也是 constant， 2也是 constant 啊，0也是 constant 啊，对不对？那它不会是0 ，Why is not 0? Why V is not 0? Constant, why is not 0? Because x1 is not 0. And x1 is a function of V, right? x1 is a function of V. If x1 is not 0, this will not be 0. Okay? So don't confuse that if V dot is 0, V is 0. No, not really. Okay? And that's because the selection of v， 因为它选这种 variable function，OK， 当它 v2 x2 是0的时候，它的斜率就会是0，大概在底部的位置。OK， so look at here, at the bottom here. So this is x2, this is x1, right? When x2 is 0, which is where? At the bottom, right? They are 3 bottoms. But the x1 value are different, which is maybe 0 and maybe minus pi and minus 2 pi and 2 pi. So there are 3 equilibrium points, okay? 这样懂吗? And this is not PD. This, as I mentioned, it's not PD, it's PSD, right? Therefore, you have multiple multiple minimas. 懂吗? So the selection of V is very important, okay? Otherwise, you create a problem. You need to solve a problem that you created, 懂吗? 这样可以想象吗？可以想象这个问题吗? So now can you imagine this? If v dot is 0, which means the slope of v is 0, right? Which could be at different locations. And at these different locations, v is not 0 because x is not 0. Okay? x2 is 0. Okay? x2. So for example, if x2 is 0, which means it's at this line, right? This line, x2 is in the direction of this, right? So x2 0 is this point. So x2 0 and x1 could be any value, which is here. So anywhere on this line, v is constant. Okay, v is constant, but x1 can be anywhere. And if you are at here, the v value is greater than the v value here. Okay, play around, okay? So the conclusion is there are many theories to tackle each of these situations. For example, v dot is equal to 0, or v dot is negative definite, v dot is negative or semi-definite. What will happen? And there are many different cases. Okay, and there are many theories to use to prove that stability. Like next time, invariant set will be 1. Okay, and that's our theory is to prove that this kind of dilemma. Okay. So that's for today.